is video C for section 3.3. Again, we're in the section for the derivatives of products and quotients. And one thing for each problem that you will need to consider is which rule do I use? Well, since we don't have a quotient in this problem, it is an obvious need for the product rule. So let's look at the derivative of the function f, and again I'm asking you to write out the steps. So step number one is to show the derivatives that you plan to take. In this case it would be the first factor times the derivative with respect to x of the second factor plus the second factor times the derivative with respect to x of the first factor. So this is the first step. Second step then is to actually take the derivatives. So we will at this point now take the derivative. So you have the first factor and the derivative of tangent x. Now again, this is in a theorem that we looked at. We did not prove any of these. Some of these you will know better than others. Others you will have to refer back to. And whether or not I expect you to have them memorized, we'll have to see how many of you seem to know them anyway. We'll take up that question when we have a quiz or a test on this. So the derivative of tangent x is secant squared x. And so this would be secant squared x plus tangent x, and the derivative of x squared would be 2x. So our derivative of the function is x squared secant squared x plus 2x tangent x. Now again, I always recommend that, well, first of all, we need to consider to do at least two algebra steps. And if you look at this, there's no algebra. Okay, so again, I want you always to go back and remember what it is that we have at this point. This is a function, and this function, I'll say function's output is the, can you fill in the next word? Okay, slope of what? Okay, a line tangent to a, good, curve at a, okay, very good. I'm assuming that you got that right, and if you didn't, you will go back and make sure that you have these four words in your definition of the tangent, or of the derivative. Now, if I want to, we could always add on to something like find the derivative at a specific point. We're not going to do that for this problem. We'll do that in other problems. Okay, continuing on with that same thought, this is exactly what I'm talking about. We need to first evaluate the derivative and then determine what the derivative would be at a specific point. So let's move that out of the way for now. And let's proceed with finding the derivative. Again, we're going to have to use the product rule on this problem because it is one factor or one function multiplied to a second one. So we take the first factor, and again this is a step that you need to write out, times the derivative of the second factor. Now is it plus or minus? And again, because it's product, and when we multiply terms of the same base, we add the exponents, which we'll add here, plus the second factor times the derivative with respect to x of the first factor. So we have sine x. Now at this point, the derivative of this is actually the derivative of sine x. So I'm going to go ahead and put that step in also, sine x, plus the derivative with respect to x of cosine x, plus, and then we have sine x plus cosine x, and then the derivative of sine x. And again, this is one of those, again, that you're going to have memorized at some point. For now, if you need it to, stop the tape, the video, and go back and look for it. Otherwise, we'll just proceed. It is cosine x. So we have sine x. Again, the derivative of sine x is cosine x. The derivative of cosine x, and go back and look at that, is the opposite of sine x, plus sine x plus cosine x, that factor, times cosine x. Okay, so the first line, we are showing the derivative. Actually, in the second line, it's a combination of showing the derivatives that we need to take and actually taking the derivative of this. And definitely down here we have then taken all of the derivatives. Now the next line, the next thing we need to do is to be sure that we have at least 2 more lines of algebra. So I'm going to use the distributive property here. So I have sine x cosine x minus sine squared x, and again I'll use the distributive property over here, plus sine x cosine x plus cosine squared x. So we've taken one line of algebra. Now at this point, I need you to think about those trig identities again. And if you look on in the front cover of your textbook, it lists all of the trig identities. Now there are some of these that you will recognize, and others of these that you will not. we're going to look at some and see if any come up here. First of all, I'm going to collect like terms, so I have 2 sine x cosine x, and then I have plus cosine squared x minus sine squared x. I'm going to put that in parentheses for just a moment here. Again, look in the front cover of your textbook. You'll notice that there is an identity. There is 2 sine x cosine x can be written as the sine of a double angle. And if we look at the statement cosine squared x minus sine squared x, we can see then that that is the another way of writing cosine 2x. So we have then that our derivative is equal to, the derivative of this function is equal to sine 2x plus cosine 2x. Now, let's go back. It says evaluate at the given point, and the given point is at pi divided by 4 and 1. So now, at the point pi divided by 4 and 1, we need to evaluate our derivative. So the derivative at pi divided by 4 is going to be the sine of 2 times pi divided by 4 plus the cosine of 2 times pi divided by 4. That would be the same thing as saying the sine of pi divided by 2 plus the cosine of pi divided by 2. Again, think about the unit circle. Where's the angle pi divided by 2? And again, it is 90 degrees, so it's right up here. The coordinates there would be 0, 1. So the derivative at this point would be 1 plus 0. Well, excuse me, I misspoke. We're actually looking at pi divided by 1/4. Pi divided by 4, And so it would evaluate to be equal to 1. So the derivative at pi divided by 4 would be equal to. Now remember, this is the slope of our original function, the slope of the tangent of our original function, not of what we see over here on the unit circle, because pi divided by 4 would be at this point. But instead, this is the slope of the tangent on our original circle. Okay, now I moved the second part of this to the next page, which says write an equation of this tangent line. In order to write the equation of a line, we need the slope and a point. Now we have our point. Our point is pi divided by 4, 1. And we have our slope as the derivative of pi divided by 4, which was, as I recall, it was 1. So if we write the equation of this line, we'd have y equals 1 times the quantity x minus pi divided by 4 plus 1, or y equals x minus pi divided by 4 plus 1. This, of course, would be the output intercept value. And so if we wanted to, we could get an approximate value for that. It is approximately x plus 0.2146. Again, I don't have that on this problem, but we could very likely look at this as an equation or a problem where I ask you to graph and to show me a graphical representation. Remember, you're going to graph this function, place a tangent at pi divided by 4. Okay, another issue that we need to talk about is this idea of second derivatives. And whereas we have y prime as the first derivative, we have y double prime as the second derivative. Another way of expressing that is f double prime instead of f prime. We can use this notation. It's a little unusual. I'm not sure who came up with the fact that you put the 2 behind the d in the numerator, but that is the recommended or the recognized notation. And then we can also use equivalently, instead of y, we could use f of x, and then the other one that we don't really use too much is that capital D. Another idea is that we can talk about acceleration. Now remember, we did mention that that velocity is the derivative of the position function. And so what we have here is then that acceleration is the derivative of velocity. So what we can say is that acceleration of time is equal to the derivative of velocity, but that would then make it the second derivative of the position function.